This is a supplementary video for lecture 19, and we will solve the following leftover problems in exercise 14, namely number 46 and number 48. So let's start with number 46. For f of x equals to natural log of x squared plus 9, we need to find the intervals of increase or decrease. We need to find local max, local min, and interval of concavity and inflection points. And finally, we need to sketch the graph. All right, so let's see how to proceed with this function. So we will start from getting its derivative. So f prime of x will be, using the chain rule, it will be 1 over x squared plus 9 times 2x. So simplifying, I get 2x over x squared plus 9. So the derivative exists everywhere because the denominator is strictly positive. So it never takes 0, so the domain will be everywhere. All right, so then we will just need to investigate where f prime of x equals to 0. So this simply means that the numerator has to be 0. And that will be the only critical number we get. Also notice that this guy exists where x squared plus 9 is strictly greater than 0. But this is always the case because x squared plus 9 is greater or equals to 9. So the domain of this function will be negative infinity to positive infinity. Okay, so then 0 will separate the domain into two parts, the part greater than 0 and the part less than 0. Okay, so it's very easy for you to tell that to the right of 0, x is positive, and to the left of 0, x is negative. And the denominator is always positive. As a result, we know that the function will be decreasing when x is less than 0 and increasing when x is greater than 0. So that will be the answer to part A. For part B, the only thing we need to do is to compute f of 0. So f of 0 equals to natural log of 0 plus 9, and the answer will be natural log of 9. And from the first derivative test, we can see that this is actually a local minimum. Let's actually keep that information over here because we will need that for graph sketching. All right, so that answers part B. Okay, so for part C, let's compute the second derivative. So this is simply going to be the derivative of this quotient, and that means we need to use the quotient rule. So we start by squaring the denominator. Then it will be low d high, so that will be x squared plus 9 times 2 minus high d low, so that will be 2x times 2x. All right, so simplifying the numerator, what I will get is 2x squared plus 18 minus 4x squared. So that way I get 18 minus 2x squared. So you could actually further simplify this guy as 2 times 9 minus x squared, and 9 minus x squared can be simply factorized as 3 minus x and 3 plus x. All right, so that's what we will get. So we get 2 times 3 minus x, 3 plus x divided by the square of x squared plus 9. All right, so again, this guy exists everywhere. So all we need to worry is where it takes 0. So f double prime of x equals to 0. So this tells me that either x equals to 3 or x equals to minus 3. So these two numbers will separate the domain into three parts. So minus 3 over here and positive 3 over here. All right, so we need to determine whether or not f double prime is positive or negative over each interval. So let's look at each factor. So for 3 minus x, we know that this guy will be positive to the left of 3 and negative to the right of 3. And for 3 plus x, so this guy will be negative to the left of minus 3 and positive to the right of minus 3. And the denominator, this guy is always positive, and the 2 over there is always positive. Okay, so from this analysis, we see that the function is concave downward at the first interval, upward in the second, and the downward in the third. So that will answer part C, first part of part C. And also we need to know the inflection point. And in order to do that, we need to compute f of minus 3 and f positive 3. So f of minus 3 equals to natural log of minus 3 squared plus 9, and the answer is natural log of 18. And if you want, you can simplify it And f of positive 3 will be natural log of 3 squared plus 9, and the answer is the same. It will be natural log of 18. So that way we see that minus 3 natural log of 18 and positive 3 natural log of 18. So these 2 points are inflection points. So we have got 2 inflection points over here. Now let's use the information we have obtained in the previous page to sketch the graph of the function. So we only need these 2 pieces of information for now. So first, the domain is minus infinity to plus infinity. So that's why I draw the coordinate in a symmetric form. And now let's actually look at the special points. So the first special point is f of 0 equals to natural log of 9. So let's say that this point is natural log of 9, and I know that my function is a local minimum. So near natural log of 9, the function should look like this. And we also need 3 natural log of 18. So natural log of 18 does not make a big difference to natural log of 9 because they only differ by natural log of 2. And the x coordinates are positive 3 and negative 3. So let me move things around so that they can look like symmetric. All right, so that's basically positive 3 and negative 3. So we know that the point given by a positive 3 natural log of 18 and the point given by negative 3 natural log of 18. Oops. So these 2 points will be the inflection points. Now let's connect these special points using the curves. And we know that the function will be decreasing in a way that's concave downward. So basically means the function will look like this until it hits the x equals minus 3. So after x equals minus 3, it will be decreasing, but in a way that is concave upward until it hits the x equals to 0. So then after x hits 0, so it will start increasing. So it will be increasing in a way that is concave upwards until it hits positive 3. And after positive 3, it will still be increasing, but in a way that is concave downward. So basically speaking, that's the graph. That's how the graph roughly looks like. Now let's proceed to draw this guy down onto the graph. So it will be something like this. So after this, it will be decreasing in a way that is concave upward until it comes here. Then after that, it will be increasing in a way that is concave upwards. And then after x equals minus 3, it will be increasing in a way that is concave downward. So as you see, I intentionally draw the graph to be symmetric about the y-axis because if you compute f of minus x, you will see that f of minus x will be the same as x squared, natural log of x squared plus 9, and they will be the same as f of x. So as a result, the function is even, and an even function should have the graph symmetric about the y-axis. On Thursday, we will discuss this point in a more systematic way. All right, so this will conclude problem 46. Please definitely try to track your work using like Desmos. So ask Desmos to draw the graph for this function, and you will see it will be very similar to what we have drawn over here. Let's look at number 48. We are interested in the function s of x given by the formula x minus sine of x, but we are only interested in this region, namely x is between 0 and 4 pi. So let's first start by figuring out the intervals of increase and decrease. So that means we need s prime of x. Well, this is pretty easy. So s prime of x is simply 1 minus cosine of x. All right, so this guy exists everywhere. Okay, s prime of x equals to 0. So this means cosine of x equals to 1. The general solution to cosine of x equals to 1 will be x equals to 2k pi. So because if you look at the graph of cosine function, it looks like this. So within the 1 period, it will be 0 and 2 pi. That's going to be taking 1 over here. But then this pattern repeats. So that's basically why you have got a k over here. For our current problem, so we are only interested in the region where x is between 0 and 4 pi. So only k equals to 0, k equals to 1, and k equals to 2 will give us a number inside this region. So that's how we obtain that x equals to 0, 2 pi, or 4 pi. But notice that both 0 and 4 pi, these guys are endpoints. So that's why they are not counted as critical numbers. So indeed, for this function, we only have one critical number, and this one critical number separates the domain 0 to 4 pi into two parts. So this is my domain 0 to 2 pi, 4 pi, and the midpoint will be my critical number. All right, so then we already have got two intervals to consider. Okay, so notice that cosine of x is always bounded above phi 1. So as a result, 1 minus cosine of x is always greater or equals to 0. And it takes 0 only at these 3 points. And for all the other points, well, so for example, over here and over here, so 1 minus cosine x will be strictly greater than 0. So that's why we know that the function will be increasing in these two intervals over here. Okay, so this is the answer to part A. And for part B, clearly from this picture, we see that there's no local max or local mean. So that's basically the answer to part B. So for part C, we need the second derivative, but this is extremely easy. So the derivative of 1 minus cosine of x will be simply be 0 minus negative sine of x. So the answer will be sine of x. So this guy exists everywhere. So all we need to care about is where it takes 0. So s double prime of x equals to 0. So this means sine of x equals to 0. Okay, so you should be familiar enough with the general solution to sine of x equals to 0. So what you should get is x equals to k pi, but we are only interested in those numbers sitting between 0 and 4 pi. So that way you will get x equals to 0, pi, 2 pi, 3 pi, and 4 pi. So those are the critical numbers you obtain from the second derivative. And notice that 0 and 4 pi are endpoints. So that's why we do not need to worry about them. So the critical number for the first derivative will basically be three numbers. And these three numbers will separate. Actually, let me be lazy. Let me just copy this graph down here. So these three critical numbers will separate my domain 0 to 4 pi into 4 parts. So all I need to do is to get the midpoint over here. So that will be pi, and that will be 3 pi. But if you proceed to draw the graph of sine of x over 0 to 4 pi, so you will see that the graph basically looks like this. And you can see that over 0 to pi, my function is above the axis, and over 3 pi and 3 pi, so the function is above the axis. And similarly, between pi and 2 pi and between 3 pi and 4 pi, so the function is below. So that's how I can see my function s will be concave upward, downward, upward, and downward over these intervals. Okay, from here, we can see clearly that all these points will be giving us the inflection points, and we need the function values. So f of pi is going to be pi minus sine of pi, and sine of pi equals to 0, so y, I guess, simply pi. So similarly, you will be able to see that f of 2 pi equals to 2 pi because sine of 2 pi equals to 0, and f of 3 pi is, again, 3 pi. So I know that pi, this is an inflection point, and so are 2 pi, 2 pi, and 3 pi, 3 pi. So these guys are inflection points. Okay, now let's copy the information we have obtained over here and proceed to draw the graph. So first, we are interested only in the parts where x is between 0 and 4 pi. So that's why when I try to draw the coordinates, I can actually draw like this. And the important numbers I have are the following. So first, so this is going to be pi, 2 pi, 3 pi, and 4 pi. And then let me actually not draw it to scale. So let me just say that this is going to be pi, 2 pi, 3 pi, and 4 pi. All right, so then the important points will be pi is an inflection point, And 2 pi, so this is not the local max, not the local mean, but then keep in mind that it has got a horizontal tangent because the derivative, namely the first derivative over here, so it takes 0 over here. So that's something you need to keep in mind. Then you have got another inflection point, namely at 3 pi. So this is going to be an inflection point. And finally, if you also compute the function value at the endpoint, so f of 0, you could see that clearly it's 0, and f of 4 pi is clearly 4 pi. So you see that so 0, 0, so namely the origin over here, and 4 pi, which is roughly here. So this guy are the endpoint function values over here. All right, so let's proceed to draw the diagram. So you could easily track that at the number 0 as well. So you see that f prime of 0, so this is going to be equals to 0, and f prime of 2 pi equals to 0, and f prime of 4 pi equals to 0. We have computed that in our previous page. So as a result, so the function will start in the following way. So since f prime of 0 is roughly 0, so we can see that locally it has got a horizontal tangent. Then after 0, it will be increasing in a way that is concave upward until it hits the number pi. So after x equals to pi, the function will be increasing in a way that is concave downward until it hits x equals to 2 pi. All right, so that's roughly how the graph looks like between 0 and 2 pi. And after 2 pi, so we know that at the point 2 pi, it has got a horizontal tangent. And moreover, it's also an inflection point. So then after x equals to 2 pi, it will be increasing in a way that is concave upwards until it hits x equals to 3 pi. And then after x equals to 3 pi, it will still be increasing, but then in a way that is concave downwards until it hits x equals to 4 pi. So roughly, let me actually modify it like this. So that's roughly how the graph looks like. All right, so this concludes the discussion of number 48. Again, please track your work with decimals. So just ask decimals to draw the graph, and you will see that it will be very similar to what we are drawing here. Okay, so this concludes the supplementary video.